All right. Hey everyone, welcome to the latest meeting of HPS San Diego. I'm going to keep this quick. Our speaker today is incoming HPS President Mike Lewandowski. Like I said, HPS President-elect. He will be speaking on radiation gauging, a practical application of basic science.
All right, thanks, Brianna. Let me see if I can get the sharing part right. And hopefully at this point, you'll be able to see the screen with the title page.
Yep, we're good.
Yep.
On my end, at
Great.
least.
Fantastic. Then if I can get this to advance. All right. So, so this is something I learned from Dr. Golden, who is a great professor, but start every session with a quiz. That way you put everybody at ease because the hard part is over right away. Okay. So I want to talk about radiation gauging. So let's put this a little bit in perspective, like why would we care about radiation gauging? So think about paper that's used in magazines, like the cover of our own health physics journal, reflective sheeting, adhesive tape, sandpaper. What do all of those things have in common? So think about that for a minute. If anybody wants to shout out an answer, Stephen, go ahead.
Hey, 6 GM.
Yeah, I'm sorry I didn't quite get that. All right, Bridget.
Thickness gauges.
Well, we're going to get there. These are all coated products. So if we have a coating, we'll want to measure the thickness of that coating. So you're exactly right. So let's talk about how we measure thickness. So going back to the earliest days when you measured thickness, you probably used some mechanical means, right? You used a ruler, a tape measure, something like that. Maybe you got kind of fancy and used a caliper or micrometer, right? But those are all mechanical means of measuring that. If you got into college, you may have used some optical methods. Does anybody remember a physics experiment where you had to measure things like maybe the wavelength of light and you used interference patterns to do those sorts of things? So there are optical measurements to do that. Radio frequency is used common. So there are a lot of places that might use a microwave beam and look at so if we look at the classic application of radar, right? So you have a beam of microwaves bouncing off something and you're measuring the time that path takes from origination to reflection to return, and that gives us a measurement of distance or the thickness of the space between the receiver and the emitter, right? There's also a way to use radiation, and that's the part that we're going to talk about a little bit tonight. So think about what we already know. Here are things that we learned in high school, or those of us who are precocious, those of you who are precocious, certainly not me, might have learned this in middle school, right? So think about the definition of density. Well, density is just mass per unit volume, and volume is just the cross-sectional area multiplied by the thickness of a solid. So we can combine those two and see that density is simply mass divided by the product of area and thickness. If we rearrange some terms, there was a reason we had to learn algebra, and that was so that we could appreciate this talk tonight. So thickness is mass divided by the product of area and density. So if we want to know thickness, so the thickness of a coating, we need to know mass, area, and density. So how are we going to measure coating thickness? I mean, if we think about something as simple as adhesive tape, right? If we want to know about how we measure the thickness of that layer of adhesive on the tape, well, I'm going to let you in a little secret. My day job is I'm the radiation safety officer at 3M, and we make tape. It's really a two-part process, right? So we have some sort of backing that's not sticky, and we add something that's sticky to it. And there you go. Now you know all the secrets about making tape. So if we want to measure the thickness of the coating, we start with knowing the thickness of the backing material, so the material without the coating, and then we measure the thickness of the coated product and do a simple subtraction. So what we need to do with this is that we need to take samples of the coated material and the uncoated material or the backing material, measure their mass, and calculate the area. One easy way to do that is to cut a circle. We learned the area of a circle, pi r squared, and I'm sure at the time you did that, you said, well, this is really interesting, but when will I ever use this? Where will there actually be a real application? Well, it turns out there are real applications for that, because if we take a circle of known area and weigh it, we can get the mass per unit area, or in this case, what we really want is the volume. So let's think about the material that we're going to coat. So coating materials usually start out as a liquid. And so it's easy to measure the volume of the liquid. Just pour it in a beaker. And then put that beaker on a scale and we can determine the mass. So now we can calculate the density of the coating material itself. Well, the mass of the coated material is equal to the volume of the coating multiplied by the density of the coating. And the volume is the thickness of the coating multiplied by its cross-sectional area. And this is where the area of that circle comes in. So if we substitute our terms, the mass of the coating is equal to the thickness of the coating multiplied by the cross-sectional area multiplied by the density. So we can rearrange some terms so that the thickness of the coating is simply the mass divided by the product of area and density. Now the thickness of the coating, or the thickness of the coated material, I should say, is actually, if we think about the mass of the coated material is the mass of the coating. So in this case, we're talking about tape. It's the mass of the adhesive layer and the mass of the backing material. So if we just want to know the mass of the coating material, so we take the total coated substance, so that's the backing and the coating, multiply the mass of the backing, or I'm sorry, subtract the mass of the backing, divided by the area, and if we keep those areas the same, it's a constant, divide again by the density of the coating material, and we end up with determining the thickness of the coating. So this is basic algebra with some measurements. So let's go back to the very beginning of adhesive tape. So adhesive tape was developed in the 1920s and 1930s. So 100 years ago, adhesive tape was developed. At this point, the way to measure the thickness of the coating was that you would start with whatever your uncoated material was. In this case, it's probably a large roll of paper or some sort of material, and you would cut a circle out of that. Because you cut a circle, you can calculate the area of the circle, and you can end up with weighing it, knowing the area of the circle. You coat the material, and you do the same thing. You cut a circle of the same area, weigh it, and now you've got the total mass. So you can go through this simple algebra process and determine the thickness of the coating. In fact, in the early days of manufacturing of coated materials, it was someone's job to go out along the coating line, the machinery that was doing this, and take a knife and cut a circle out of this moving material. Reach into the machine and grab the sample that you just cut out, take that back to the laboratory. cut a circle of known area, weigh it, go back, cut another sample of the coated material, go back to the laboratory, cut a circle of known area, weigh it, do your algebra. And at that point, you could determine the thickness. Very simple process. You can get anyone to do this with a simple algebra and some simple techniques. So why would we change that? Well, to start with, this is all destructive testing. You can't sell the samples that you're taking. And if you want a high quality product, you have to take a lot of samples, which means you end up damaging whatever it is you're trying to manufacture. The other thing to think about is that there's a big time lag between when you take the samples and when you get the results. So think about this. You walk out to the manufacturing line, you cut your sample. You walk back to the laboratory, make your measurements, do your calculations, compare it to your tolerances, go back out to the coating line, and you tell the person that's operating the coating line what adjustments they need to make to the equipment. And then you take another sample and you go back to the laboratory and you cut the sample, you make your measurements, compare to the tolerances, provide feedback back to the manufacturing line, and you do this all day long. So you end up with large swings in your behavior of the thickness until you finally dial that in, and then you get the machine working just right, producing exactly what you want. Not too thick, not too thin. And everything is great until there's a change. Like you run out of the batch of adhesive and you introduce a new batch of adhesive which might have slightly different properties. The density might be slightly different. Or you run out of a batch of backing material. And then you have to sample the backing material. And you start all over. So you start with big swings, you dial it down. And then there's a change and you have big swings and you dial it down. So you end up with a sawtooth curve of quality. Another thing to think about is that this is a full-time job for someone. Going out, taking samples, coming back to the laboratory, making the measurements, providing feedback, back and forth all day long. But what's most important is that this is a potentially dangerous job. So think about acquiring the sample. You're walking next to this manufacturing equipment, which is making tape in a large or whatever it's making, whatever the coated product is, it's making it in a roll-to-roll process. So you start out with a large roll of backing material that you run through, you coat it, you run it through equipment. So there's coating, there's drying, there's who knows whatever, many processes that occur. And this is all moving over time faster and faster and faster until today's processes run at hundreds of feet per minute. Your job is to reach out with a knife, cut by hand a sample, and then reach into this moving equipment and retrieve that sample. Now think about if we're coating something that's an adhesive, that means we're coating something that's sticky. So the chance that your knife or your hand might touch the sticky part and get pulled into the machinery. So this is really a potentially dangerous job. So there's got to be a better way, right? So think about different ways to make measurements. Well, there's mechanical measurements, right? So maybe we could have a machine that would actually measure the thickness of this material as it was running through. But mechanical measurements are typically contact measurements. Think about calipers and micrometers. They're touching the material. So it becomes really difficult to touch things which might be sticky or gel-like or liquid. It also becomes difficult to touch things that are moving. You could end up tearing it or leaving some defect, doing something like that. Well, what about optical methods? Maybe we could use light, shine light through that and measure interference patterns or something like that. Well, actually, optical measurements work really well for things which are optically clear or even things that might be translucent, but they don't work well for things that are opaque. So think about duct tape. You can't shine light through duct tape. Think about paper that's coated to be the cover of a magazine. You can't shine light through something which is opaque. Maybe there's radio frequency methods. So maybe you could shoot microwaves at this and measure um, the difference between reflections from the top surface and the bottom surface of a coated material. In fact, there are ways that are being done now using very high frequency terahertz radio frequency waves that do time of flight measurements and take reflections from every change uh, in the density of materials. And those things work really well unless the material you're trying to measure either reflects or absorbs the radio frequency radiation. So anything with a metallic content or a water content is unsuitable for using radio frequency measurements. So this takes us to thinking about radiation. So we know radiation is absorbed by matter. And for photons and thin materials, there is an exponential equation which defines that attenuation, that absorption. Here's another quiz. So Rankine discovers X-rays in 1895. So when does this exponential equation I equals I naught e to the minus mu t, when does that first appear in the literature? And for bonus points, what's the name of this mathematical relationship? So go ahead, put your answers into the chat. And let's see if you get bragging rights. All right. So if Rankine discovers X-rays in 1895, Ken posits that by 1896, this exponential equation shows up in the literature. All right, so we've got a lot of great answers. Let me reveal the answers here. Well, starts out that in the early 1700s, scientists were interested in light. And a couple of early experimenters, Pierre Bourget, in the early 1700s, was investigating the absorption properties of light using colored liquids. And Johann Heinrich Lambert followed up on that in the mid 1700s. So it turns out in the mid 1700s, the middle of the 18th century, 150 years before Röntgen, the Bourget-Lambert law was described in a paper that talked about the intensity of the light traveling through an absorbing liquid was related to the initial intensity with an exponential attenuation based on alpha, which was a constant, a property of the material that was dissolved in the water, and the distance through which the light passed. So this was a theoretical construct in the mid 1700s. 100 years later, August Beer actually does an experiment which confirms this theoretical equation. And the Bourget-Lambert law has been referred to as the Bourget-Lambert-Beer law, or more commonly, Beer's law, to describe this property of light passing through some sort of attenuating liquid. And this is something that chemists use now in spectroscopy. So the theory shows up 150 years before Rankine, and Beer's law shows up 50 years before Rankine. So let's see how we can apply this. So probably the easiest way to think about this is, let's just take a radiation source, a photon emitting source, and place a detector opposite it. And we can measure the unattenuated beam, so I naught, and then put some material in between and measure the attenuated beam, I, and then we're able to derive the thickness, or quite simply, we could sense the difference between having nothing in between our radiation source and the detector and having something in between the radiation source and the detector. So this is the first application of something which might be called a level gauge or a nuclear switch. And it's in the most basic process, it's just simply detecting that there's something present or there's something absent. So the diagram on the right-hand side of the slide illustrates a radiation source and two detectors, a high-level detector and a low-level detector. When there's material in the vessel that covers the low-level detector, that tells us that there is something at that level. And then as that material increases into the vessel, and it then covers the high level detector, which tells us that the level of the material is up to the higher detector, that gives us an opportunity to stop filling the vessel. So this is a way to keep from overfilling and spilling chemical materials. So this is an excellent way to make sure that oil refineries don't overfill tanks and leak petroleum products all over the environment. And it also gives us an opportunity, if we're doing some chemical processing and this is a tank full of raw material, that as the tank reaches down to that low level and empties to that certain point where it uncovers that lower level detector, tells us to open a valve and refill the tank so we do not run out of whatever this material is we need for our chemical process. So this is a simple application of this Beer's law. So how are these level gauges used, right? So I've talked about preventing overfilling, automatic filling of process vessels. Another way to think about this is that there's certain quality control on filled containers. So think about this as we start out with just simply looking at a point source and a detector. And when the level rises to a point at which that the material obstructs that beam, we know that the container is filled to that level. So we can do this for tanks of petroleum, we could do this for tanks of chemicals, but more importantly, we could do this for small 12-ounce containers. So how many times have you opened up a can of your favorite beverage and not given any thought to the fact that you're getting a full can? It's not Russian roulette to determine as you pop that top to say, am I getting a full can or is it going to be a partial can? Well, there are devices which are used with just a simple point source and a point detector that are used to determine whether those cans, as they run through the bottling plant, whether those cans are full or if there's been a problem and they're not completely full. The ones which are full get packaged up and go to the grocery store. The ones which are not full get rejected and they go off to themselves. So this is the simplest way to do this for a level gauge is to use a point source and a point detector. So how many of you learned how to calculate the intensity and perhaps even explore the inverse square law considering a point source and a point detector, right? Simple mathematical processes, things you learned early on in your career as a health physicist. And then you had a professor who decided to make things just a little more challenging. And you had a point detector, but now you had a line source. And that's the illustration that we're looking at in the center, where instead of having a point source, now we have a line source, which really is just a whole series of point sources that we can use calculus to combine the effect, right? And then you said, well, this is why they're making me take calculus, so I can solve this problem. And that gives us a little better way to measure the level of the material. Instead of just saying it's full or it's not full, now using a line source and a point detector, we can get some feeling for how full is this container. And if we want the best measurement, we have both a line source and a linear detector. So line source and line detector, I haven't even done the math, but I'm sure it's scary. But that gives us the best way of figuring out just at what level is the container filled. All right, so this is a little segue, okay? All very interesting, I'm sure, but this, what does this have to do with measuring thickness? This is simply a nuclear switch telling us whether some container is full or not. Let's go back to some algebra, right? So Beer's law, the ratio of intensities is exponentially related to the thickness. So let's take the natural log, let's rearrange some things. So we end up with the natural log of the ratio of intensities is equal to minus mu t, where mu is the property of the absorbing material, t is the thickness of the material. Well, thickness is just mass divided by the product of area and density. So if we start throwing these things in and rearranging some terms, we can see that the natural log of the ratio of intensities is equal to minus mu over rho. Is that familiar to anyone? Multiplied by 1 over the cross-sectional area, multiplied by the mass. So the natural log of the intensities is proportional to the mass. Now we're talking about measuring mass. This gets us to an application called the nuclear scale. So let's take this level gauge and let's rotate it 90 degrees. And instead of measuring horizontally, let's measure vertically and let's measure the material that's passing over it. So let's take our friend a conveyor belt. Let's place a radiation source on one side of the conveyor belt and a radiation detector on the other side. And it turns out that if we look at this exponential equation, and if we take the natural log, we end up with something which is linear over, roughly linear over a certain region of masses. And if we stay in that mostly linear area, we can measure mass based on the ratio of intensities. So this is a situation where we can continue with our gamma emitting materials and we can measure mass. So what sort of things would we measure with nuclear scales? Well, rock, the previous picture that we saw, is rock that's running on a conveyor belt through some sort of processing plant. We can measure many rock plants that are used for crushing stone for concrete or various other applications, including roofing shingles. Measure the mass of the rock using a nuclear scale. Coal-fired power plants measure the mass of coal that's running into the burner using these nuclear scales. And if they know the mass or the rate at which the coal is moving into the burner, and they can vary the rate at which that coal is moving into the burner, they can control the amount of heat that's created, thereby controlling the amount of steam, thereby controlling the amount of electricity that's being generated. So these are all opportunities here. Wood chips and biomass that are going into similar types of burners our digesters are measured that same way. Fertilizer, sand, salt. Again, simple matter of we could do this with a point source and a point detector, but because we're looking at bulk materials, bulk properties, and we want to measure the mass more accurately, we start with something simple like a point source above the conveyor and a line detector below the conveyor. And we can get good measurements. If we use 2-point sources and a line detector, we can get better measurements, but it turns out that the best measurements come from having a line source under the conveyor and a point detector above it. You learn that line source problem and when you were studying health physics for a reason, right? It has great applications, although at the time, the only application that was ever offered to us was here's a pipe full of radioactive liquid, and you're standing next to it in your nuclear plant. Yeah. All right, so we're measuring something, but are we getting any closer to measuring thickness? All right, let's go back to thinking about the problem. So if we're talking about measuring the thickness of a coating, well, Beer's law was derived for photons, right? It started with visible light. And a photon is a photon, so we can apply it to higher frequency photons, to gamma rays or X-rays. Turns out that Beer's law also applies to electrons. So think beta particles. So looking at the math, we're going to rearrange the math just a little bit so that the natural log of the ratio of intensities is equal to mu over rho. So these are properties of the material multiplied by the ratio of mass to cross-sectional area. So in the coating industry, the mass per unit area is called basis weight. So let's take a beta thickness gauge. So in this case, we're starting with a radiation source, something that emits beta particles. Those beta particles transmit through some material we want to measure, this coated material, into a gas-filled detector, typically an ion chamber. As the beta particles ionize the gas, the applied voltage attracts the ions to a central cathode. We end up getting some sort of either a current measurement or a pulse measurement, which gives us a measurement of the amount of beta particles that are being passed through or transmitted through the material. So the larger the signal, the less attenuation is occurring. So it turns out that this is also a situation where over a certain range of basis weights or mass per unit area, there is a linear part to the curve. Commonly used isotopes, beta-emitting isotopes, are promethium-147, a relatively low energy, maximum energy 224 kiloelectron volts. We use a high energy beta particle, strontium yttrium-90, with a maximum energy 10 times that, 2200 kiloelectron volts. And then krypton-85, which has a maximum energy about 670 kiloelectron volts. And those three isotopes let us measure over a useful range of basis weights. And basis weights are given in terms of grams per square meter. Now, how many of you intuitively know how much a pound is? And how many of you know what a kilogram is? But who knows what a gram per square meter is? Right? So that's one of these units that's used in a specific industry. And if you're outside that industry, who knows what that means? All right. So for perspective, newspaper. Newspaper is a relatively thin paper, and that's in the 35 to 55 grams per square meter. Notebook paper, the paper that you used when you were in school, that's about 70 to 90 grams per square meter. So almost twice as thick as newsprint. Office printer paper is 90 to 100 grams per square meter. Okay. If we get to, so the cover material on like the Health Physics Journal or other magazines or journals, that's in the 100 150, 200 gram per square meter range. If we get up to about 400 grams per square meter, now we're talking about business cards. Not quite as flexible, right? So thicker materials. So that gives us a sense for that. If we want to measure thin films, thin coatings, thin materials, like newspaper, we would use Promethium 147. If we want to measure business cards, we would use Krypton 85. But if we want to measure really thick stuff, that's where we would run to strontium 90. So think about, thick materials or plastic materials, things which are more rigid. Then we'd look at strontium 90. Vinyls would be a good application. So this is what a beta thickness gauge looks like. They're really boring. The radiation source sits in a box, so it's got the radiation source and a safety shutter to terminate the beam. And directly opposite is an ion chamber and a preamplifier, and they pretty much look identical. There's nothing special to look at. But if we think about the radiation gauge, in this case, where we have the beta source and the detector opposite that, if we place those on a frame, which has some mechanism in it that lets these two components scan back and forth across the material, we can now go back and we can measure the thickness of our coated material from edge to edge, not just where we can reach to take a sample. So we can actually measure the entire material. And because we're doing an electronic measurement, a non-contact measurement, we're not just causing any sort of destructive testing, right? Because it's electronic, we can actually determine that I to I naught ratio immediately, do the calculations through the computer, make a comparison to the tolerance, and all that happens immediately. And then we can tie this equipment into the coating head, the part which is releasing the material that's being coated on our substrate. And that can happen in an immediate situation where there's no longer a time lag between taking our sample, determining its thickness, and then providing feedback to make an adjustment. All that can happen immediately. So we can eliminate the destruction, we can eliminate the time lag, and we can dial in much tighter tolerances much faster. Now, the downside to this is that we're eliminating a job. There's no reason for someone to go out and take those samples. The equipment does it. It turns out we're not really eliminating a job, we're just changing the job. We're changing it from this relatively low-skilled activity to now we need someone who has to do the programming, who has to understand the programming, who has to maintain these thickness gauges. So we have upskilled the requirements for this job. So what do we measure with beta gauges? Well, turns out that we measure just about every paper product that's manufactured, because almost every paper product is coated with some sort of material. So all of our the paper that we use for our inkjet printers has a thin layer of a clay coating so that the ink doesn't bleed into the paper, so that we get a nice crisp print. If we want colored paper, that's a coating situation as well. So coatings on paper and cloth, including adhesive tape. So the thickness of the adhesive on this tape is measured using a beta gauge. Extruded and blown films. So thin films, things like the cling wrap that you might use on your leftovers. The thickness of those films is measured using radiation gauges. Coatings on films and vinyl and other plastics. So what we're looking at right now is we're looking at a faux wood grain print that's coming through this coating process, and the thickness of the coating on that vinyl is being measured with the beta gauge. So a lot of things that we use in our everyday life are brought to us through the application of radiation gauging. But lest you think that this is all simple applications, we can also do environmental science with beta gauges. We're just going to sort of change the size and scope. So a lot of aerosol mass measurements are being done using automated mass measurements. So PM10, PM2.5, a lot of those measurements for environmental science are being done using something called a beta attenuation mass monitor. So in the late 1970s, early 1980s, there were papers that were published as the EPA was exploring ways to monitor and control aerosols and nuisance dusts in the air around industries, construction, and other industries. And it turns out that this beta aerosol mass monitor was a great application. So this particular device uses a small chlorine 30 or carbon 14 source, microcurie levels of carbon 14, and things like a fiberglass film in a roll where the thickness or the amount of attenuation caused by the clean filter material is measured, and then air is pulled through that filter material, and aerosols are deposited on that filter material, and then that coated filter material is measured again, and the mass of the material which has been deposited on the filter is measured. So what we're looking at on this slide is a large unit which might be set up in an air monitoring station. It may be put on a tripod. It may be permanent or temporary. This technology has also been miniaturized so that a worker can wear a small device like this on their belt to do personal monitoring of the particulate load that they're being exposed to. All right, so if we go forward and talk about more science, so we talked about beta particles, let's go back to gamma rays again. And if we think about the distribution of Compton scattered photons, you might remember the Klein-Yashina formula. Or you might be like me and you have to look it up. You remember the name, but the math is an old friend which you haven't talked to in decades. So you can look that up. What it tells us is that the probability of Compton scattering is proportional to the atomic number. And it also tells us that large angle scattering decreases with the energy of the photon. So if we think about this, if we have photons which are being emitted toward a material, and that material has a high atomic number, and the photon energy is low, there's a greater probability that those photons will interact with the material and get scattered back toward the direction they came from. So we can use this application for one-sided measurement. So in this case, if we have and I'm going to try to illustrate here, if we have a radiation source that emits low energy gamma rays, for example, americium-241 with 59 kiloelectron volt gamma rays, surrounded by a radiation shield, which is surrounded by a scintillator. So the gamma rays are emitted towards some material we want to measure. We're choosing a low energy photon, so that will maximize the probability of high angle scattering back toward us. If we're measuring moderate atomic numbers, we will actually get a relatively large number of photons back scattered, intercepted by the scintillator, converted from photons that we can't see to photons that we can. So blue light, or some cases, some ultraviolet. That light can impinge on a photocathode and be converted to electrons, which are multiplied in a photomultiplier tube, and we end up with an electrical signal. The size of the signal will be proportional to the number of photons that are scattered back, i.e., proportional to the mass of the material in front of the radiation gauge. And again, over a defined period or range of masses, we get a relatively linear signal. So this is a situation where we can do one-sided measurement, and these gamma backscatter gauges do a great job in measuring the thickness of coatings or extruded material that are too thick for beta gauges to measure well. So films up to 2,000 grams per square meter, and beta gauges, are really good at measuring less than 2,000 grams per square meter. Extruded PVC, so the thickness of PVC pipes is measured and monitored using this type of radiation gauge. Rubber, if you're thinking about layers of rubber, which are also monitored using this kind of one-sided measurement, and we can actually measure the thickness of mineral. So if we have heavy sandpaper, so we have a heavy backing material that might be 500 or 600 grams per square meter already, and then a layer of resin and a layer of rock on top of it to create some heavy duty sandpaper. So we can measure 1,500 to 8,500 grams per square meter. So now we're measuring things which are not very flexible. And non-woven fibers. So does anyone know what a non-woven fiber is? You all, since 2020, you all have had lots of experience with non-woven fibers. The filter material in the disposable N95 masks that we all got to wear, okay, those are non-woven fibers. So this is a situation where we have the ability to measure the thickness of coatings and extrusions using this one-sided measurement. So let's talk a little bit about the radiation safety concerns. So during use, there is really minimal exposure to the people using these radiation gauges. So much less than a millisievert per year or 100 millirem per year. Even for individuals who are doing regular and predictable maintenance. So these are folks who might be cleaning these devices, they may be doing calibrations, there may be situations where they're actually installing or relocating these devices. All these devices have the ability to terminate the radiation beam by using a shutter, a lead shutter or a tungsten shutter. Even folks who are handling these devices are exposed to levels of radiation which are generally less than a millisievert per year. What we have to be concerned about is accidents that would lead to shielding loss or source rupture. So we have to think about our gamma sources are often special form. So they start as a non-dispersible ceramic or metal and are generally doubly encapsulated. So we don't have to worry about a release or contamination event from a gamma source unless that source capsule is breached. So unless we are cutting or drilling into that source capsule, radiation gauges have a very low potential for any contamination events. Now we contrast that with beta sources. So beta sources have to have a very thin metal film exit window to allow beta particles to come out. And some of those sources, like krypton 85, are gas sources. So think about situations where you have a gas of a specific volume confined within a metal container that has a very thin metal film. If that were to heat up in the case of a fire, if we increase the temperature of a known volume of gas, what happens to the volume? So if we increase temperature and keep volume the same, pressure has to go up. But if the pressure increases too large, then the seal between that thin metal film and a sturdier metal container will rupture, and we end up venting the gas. We also have to be concerned about shutter failures or shielding failures, and then loss or theft. Many of these devices are used in situations and environments, particularly our friend, the level gauge or the nuclear scale. These are located in places where people are not frequently there. So there's a situation where things can be lost or stolen without folks knowing about it right away. So these are sort of the concerns that we have to think about. And that's the opportunity for an industrial health physicist, right? So there's licensing associated with all radioactive material devices, whether it's a specific license, which allows the licensee to do maintenance and other sort of service activities, or they're used under a general license. Someone needs to understand what the licensing parameters are. And regardless, there needs to be a radiation protection program developed and implemented. All of these devices require physical inventory and safety checks, typically on a 6-month basis. There are surveys, so dose rate and contamination surveys, like leak tests, that happen on, so the dose rate surveys typically happen on installation and removal from service. Our leak tests happen on frequencies anywhere from 6 months to 3 years, depending on the device. The workforce needs to be trained, particularly people who are doing maintenance activities and are actually handling the device. When we're adding devices or getting rid of devices, there's packaging and shipping that requires some special knowledge to do that safely and legally. There are audits that occur, and the most exciting thing for any health physicist anywhere is responding to incidents. And really, the goal for all of us as EHS professionals is to make our lives as boring as possible, right? Because when we're responding to incidents, that's where things get really exciting. All right, with that, I've come to the end of what I have to talk about with radiation gauges. I do have some things to talk about from the Health Physics Society, but I'm going to pause for a minute to take any questions that you might have about radiation gauges.
Thank you, Mike. I had one question. You said when you were talking about the nuclear scale, you said that ultimately it was determined the best configuration was a linear source with a point detector.
Yes.
Why is that?
Well, it's a great question, Ken, and I'm not entirely sure the answer to that, but I think it has something to do with the fact that um, in those conveyor type of applications, you don't have a uniform thickness of material you're trying to measure. So in this situation where you've got a lot of photons that are available from a linear source distributed over sort of the cross-sectional thickness of the material. And it turns out that um, the I think it's related to partly to signal strength, and other part of it is I believe, and I'm not an expert in this area, right? I'm an expert in the safety of gauges, but not in the actual technology of the gauges themselves. But I believe it's related to a situation where you have this non-uniform distribution of mass. And so that linear source tends to,
Did they average it out more or
so
something?
yeah, exactly, averages it out and gives a better measurement of that entire bulk mass measurement.
Okay. And then just one follow-up question on the one where you showed I think it was the beta thickness gauge. And you showed the kind of the two halves of it. Is it actually like moving back and forth across the sheet? How fast does it move? Does it move very fast, or is it just randomly
Um,
zigzagging back across the width of the
yeah,
sheet?
so um, the speed at which it moves is relatively slow, I guess. So example, I'm going to just sort of move my hand at the typical speed of a beta gauge, right? So that's it's that there's a relatively large amount of mass associated with some of these things. So they move at a stately speed, but a consistent speed as they move back and forth in measurement. Once you stop doing the measurement, then they can move about twice that speed to, come off the material and get parked off to the side for something. But during the measurement process, they move slower than they actually move when you're just moving them from place to place.
Yeah, okay, yeah, that kind of makes sense. Almost kind of like when you're frisking a surface with a little
Yeah,
Geiger-Muller counter. If you move too fast, you're turbo frisking it, right? Yeah,
yeah,
okay.
exactly. Good.
I have a
So
question.
Mike, oh,
Oh,
Yeah.
go for it.
should I go first?
Sure.
I could expand your concept and say there must be a neutron gauge also, or there must be also a neutron gamma gauge. And I know in science there are neutrino gauges that measure the empty holes inside of pyramids. Do you have any experience or know of any applications of using other alpha gauges or neutron gauges or N gamma gauges or neutrino gauges?
Yeah, so gamma and neutron gauges are often used in geotechnical applications. So there's moisture density gauges which use both gamma and neutron to measure the level of compaction that's in road surfaces and other sorts of materials. And those are the gauges which are lost or damaged frequently. So if you go and look at, either the state or the NRC's, nuclear incident reports, you will find on, a monthly basis the reports of loss or damage to these moisture density gauges. Neutron gauges are also used in borehole or well logging applications to determine the types of layers of rock. So both for oil exploration as well as for other types of, geotechnical measurements. But I don't have any sort of experience using those types of devices, in the field that I've worked in for the last 30 years or so. It's been beta and gamma, strictly for those types of measurements, and not anything in terms of, having needing anything that would require neutron measurement or those sorts of things. And I am totally unfamiliar with neutrino gauges and those sorts of applications. Okay. All right, Bridget, you had a question, and then I think we're going to
Yeah.
dive on to the next part.
Perfect. I teach a lot of nuclear gauge users, actually. Everything from concrete folks to manufacturing and fill level gauges. And one question that I don't know if I have an answer for, and I'm kind of curious about, in the event of a Krypton 85 gas rupture, just how hazardous is that? Because wouldn't the Krypton 85 gas just, leave into the environment? I don't know a ton about that, so I was just
Yeah,
curious.
so great question. And so my employer uses hundreds of Krypton 85 gauges, and generally speaking, a loss of a Krypton gauge source integrity is kind of a non-issue, right? So Krypton being a noble gas, it's not chemically reactive. If you were standing next to this, you would breathe it in, you would breathe it out. You'd need to be concerned about beta exposure for that period of time when the krypton was inside you, but once you've exhaled it, it's not really an issue. Obviously, if you're standing in a cloud of a beta emitter, you have to worry about skin exposures. But generally speaking, in industrial environments or there's usually sufficient ventilation going on because you need to control all of the other stinky stuff that's happening in these processes. So it turns out that the volume of air exchange and dilution really is the solution to this pollution. So it turns out that it turns out to be an insignificant health risk for these sorts of things. Generally speaking, unless there was some sort of catastrophic event, if a krypton source was going to leak, it would probably leak over a period of time. So you wouldn't have a large source term. You wouldn't have, and the activities for krypton gauges run anywhere from 200 millicuries up to about 1.2 curies. So they vary widely in terms of that. And so it's that's not the situation that would keep me up at night.
So in the event of a catastrophic event, the emergency
Yeah.
response would be to evacuate
Yep.
the area, to aerate it, and maybe monitor for beta contamination, possibly.
Well, it's again a noble gas, so you're unlikely to have any beta contamination, right? So there's
Okay.
so the krypton itself is not going to be attracted to anything. It's not going to stick to things.
Yeah, that makes sense.
Yeah, so that's a situation where contamination monitoring is always a good idea, but it's unlikely to be particularly helpful for a krypton release.
Gotcha. Thank
Okay,
you so
great.
much.
Yeah, you're welcome. All right, so I do have a few things to talk about, some news from the Health Physics Society. So if you'll bear with me for another, 10 minutes or so, we'll go through that. And before I continue, anyone else who's got questions that they didn't have a chance, or if a question comes up later,
Excuse
um,
me, excuse me.
yeah.
I don't have a question, but I just want to say for Bridget's question, anytime there's an accident, first thing you do is treat injuries. You don't worry about exposure and stuff. You treat the injuries.
Yeah,
Yeah,
good point,
you're
Ellie.
you're exactly right.
I work at a hospital.
I got one more question before you go on. Is there any way, any of these devices that measure roughness? As you say, some of these things have a roughness to them, so that they may, something that's thicker may have variable, maybe is intentionally designed to have a variable thickness. Is there any of these gauges that are able to measure the 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 smoothness or the roughness of a layer?
So I am unaware of any radiation gauge that measures that sort of property. These are all measuring relatively bulk properties.
Mhm.
So anyone who's got other questions, feel free to email me after the fact, and I'll do my best to answer those questions. So let's talk a little bit about what's going on with the Health Physics Society. As Brianna noted, I'm the president-elect of the Health Physics Society, so I would be remiss in my duties if I didn't talk a little bit about what's going on at the mothership. So to start with, right now, the big project we're working on is a redesign of the website. So if you've been on hps.org lately, what you're seeing today is going to look a lot different than what you will see in 2 or 3 months from now. So it's an entirely new platform that's being put together. We're going to use the XCD platform for keeping track of membership information. And if you have registered for a health physics meeting or used the meeting app at an annual meeting in the last couple of years, you're familiar with XCD. So we're going to take that person information, connect that with the WordPress platform, and rebuild the entire website. And that will give greater functionality and modern functionality, so it will be mobile friendly. So it will look good on your phone or your tablet, not just on the desktop computer. There's going to be better search capabilities, and I realize that's a low bar with our existing website, right? But it's going to be, you're going to have the ability to find the things that you're looking for, and it's going to be much easier for us to maintain. Therefore, we're expecting that things will be up to date, faster, and we'll be able to pull some things together. So what I'd like all of you to think about is, what sort of resources would you want for your chapter on the new website? So we're starting with right now, we're building the HPS website, and then the second wave will be building websites for chapters. So that the same technology advancements will be pushed out to chapters as well. So for example, if your chapter is now on the HPS chapters.org site, it'll be moving over to this new platform as well. So think about what sort of resources you want at the chapter level, and think about what changes, one or two changes that we would do to the website, which would make a difference to you. So again, provide that feedback later. We'll get an opportunity at the end. So also the other things that are happening is that the journal went online only at the beginning of the year. So no more paper copies are getting sent out. Everything is online. One advantage of doing this is that we no longer have to charge page charges for publishing in the journal. So if you've got some ideas from everything from an operational topic to publishing the research that you've been doing, now's the time to take advantage of this, because the barriers have been removed. So there's no longer a financial unincentive for publishing in the journal. We're also working on updating the contact information. So I've listed on the slide what's listed on the website right now. So it seems like that we've got the right people listed, but if there are any problems, any changes with this, let us know right away. So you can send that updated information to the web editor, or you can send it to me. Probably the easiest way to update that contact information is to submit a chapter report and then identify the current officers. And just as a reminder, the chapter presidents need to be HPS members. So I bet there are a number of folks who are on this call who are not an HPS member, and I want to encourage you to join HPS. So you're a member of the San Diego chapter because it helps build your professional network. It gives you somebody to call when you need some help. It helps you expand your career opportunities. Well, these are the same reasons to join HPS. But now, instead of just having a smaller geographical area, you have the entire country to draw from. You'll gain access to resources, you make friends from all over, it gives you a chance to engage socially and intellectually, and you'll be able to make a difference by participating in activities that are sponsored by HPS. So what are you going to get for your membership fees? Well, to start with, you get the Health Physics Journal, Operational Radiation Safety, you get the HP News newsletter, you can sign up for and receive at no cost newsletters from our ERPA affiliates, like the Canadian Radiation Protection Society, the French and the UK societies. If you're studying to be a certified health physicist, there are Part 2 questions and answers that are available. And all HPS developed ANSI standards, so the N13 and the N43 standards that are developed by HPS are available for free. There are many NCRP reports and commentaries that are available for free. And there's an HP toolbox that has a whole collection of resources that might have some interesting applications to what you're doing. The jobs listing is set up, so it's a great job board. So if you're looking for work, or if you want to hire somebody, it's a great opportunity. And then the last thing I want to point out is just recently was announced, there is a CHP prep course that's sponsored by the early career section of the HPS. So if you're an HPS member and a section member, you can attend that CHP prep course for free. So there are some things that are not free, but highly discounted. So for any NCRP report that is not available for free on the HPS website, you can buy that report for 30% of the list price. So you get a 70% discount. ICRP publications are 75% of the list price, so a 25% discount. More information on that is coming. We're trying to work out the details in terms of how you go to the HPS website and purchase this and get the discount. So that's still a bit of a work in progress. If you're a closet physicist, you can subscribe to Physics Today for $25 a year. You get a reduced rate to attend an HPS meeting. In fact, that reduced rate is the cost of membership. So right there, just attending an HPS meeting, that you'll break even on your membership dues right at that point in time. If you attend a Radiation Research Society meeting, you get a break on the registration fee as well. And you will get membership in the International Radiation Protection Association in IRPA for free. So I want to encourage all of you to get involved. So join a committee or a task force. Go to hps.org, click on organization, click on committees, read through the descriptions of committees, and any committee that looks interesting to you, there will be a button that says volunteer for the committee, right? So you'll be able to contact the individuals and volunteer for that. You can reach out directly to me if you want. I'd be happy to find a place for you to get involved with HPS. You can also join a section. So the sections are topical, as well as we have some non-topical sections, or I guess multi-topical sections, like the early career section. So if you're just starting out in your career in health physics, this is a great opportunity to get connected to a group of folks just like you and help to build those networks and build your career in radiation protection. There's also a women in radiation protection section that is geared up to provide a community for women and who are looking at their own unique challenges in a male-dominated science field. You can become a mentor or you can get a mentor. So go to hps.org, members only, and click on the mentorship tile and volunteer to be a mentor. Share your experiences with someone coming into the field or gain a mentor, regardless of what level you're at in your career, both for experienced folks as well as for folks who are new. I want to encourage you to nominate someone, including yourself, for a leadership position. So every year we're looking at electing officers and directors to the board. So Craig Little is the chair of the nominating committee. So contact Craig to nominate someone or to nominate yourself. So I just want to point out that there are some things that are coming up. So in 2 weeks, we have a chapter council meeting. So that's a virtual meeting that is set up for chapter leadership or chapter members to attend, to find out what's going on in other chapters, to share what's going on in your chapter, to learn about resources that are available to chapters, as well as to ask others about the challenges you're facing and how they are facing those same challenges and how they are solving those things. The third annual HPS Winter Workshop, which this is what used to be called the mid-year meeting, that's happening at the end of March at the University of Alabama at Birmingham. So registration information is up right now for that. The topic is fusion and non-ionizing health physics. It looks like it's going to be a really great day and a half winter workshop, immediately followed by a professional development school on non-ionizing radiation. And if you sign up for both the workshop and the professional development school, you get volume pricing. So there's a reduced price for that. The registration information is available right now on hps.org. So that non-ionizing radiation professional development school is I've seen some preliminary discussions of the agenda, and it's going to be a fantastic experience. So if you're involved in non-ionizing radiation protection, this is a great opportunity, and they do not come around very frequently. So this could almost be a once in a generation opportunity here. Finally, I'd be remiss if I didn't pitch the HPS 70th annual meeting, which is this July in Madison, Wisconsin. That's my local chapter. So please come visit us in Madison in July. There will be beer and cheese. Do I need to say any more, right? All right. So I want to sort of end with a little bit about who I am, right? And what you can expect from me as the president-elect at HPS. So I'm a kid who grew up in Wisconsin and had no idea what health physics was. I started my career as a physics student and double majored in physics and math. And I went to this small state school, and it turned out that in my physics department, I had two physics professors who were health physicists and got introduced to the field of health physics. I started my career as a high school physics teacher, went back to school, got a master's degree in health physics from Purdue. I've been an HPS member for more than 30 years. And, with this experience, I worked on uranium mill tailings to start with. Then I went to the waste isolation pilot plant. So I went from standing out in the beautiful southwestern United States with lots of heavy equipment running by, spent the next period of my time half a mile underground in a salt mine, and then I ended up at 3M, and I've been at 3M for almost 30 years. I'm the corporate radiation safety officer and manager of the radiation safety group there. I'm a certified health physicist. I'm an HPS fellow. I'm on the NCRP. I've had a lot of experience with decommissioning and radon, and obviously fixed radiation gauges, radiation machines, non-ionizing radiation. 3M did operate a wet storage, category 4 wet storage panoramic radiator, actually operated two of those for a while. Those were really interesting and a lot of fun. So I have a lot of experience in the manufacturing environment. 3M is also a huge technology company. So we have an R&D environment with about 50 distinct laboratories using radioactive material and radiation machines and non-ionizing sources. A lot of interesting things like that. Regulated by NRC, agreement state. I've had experience previously with Department of Energy. So I've kind of seen a lot of things, over my career. Personally, I'm a Wisconsin native. I'm married. I've got two adult children. I've tried to talk both of them into becoming health physicists, and they both rolled their eyes at me. One wants to be an astrophysicist. The other one is in graduate school for clinical mental health counseling. I have no doubt that she will be writing papers, and I will read those papers and recognize that I have been a case study for her entire life. So I'm happy to be of some service to her for that. So what you can expect from me is I have been involved in HPS strategic planning for the last 10 or 15 years. So I'm going to focus on moving HPS toward its vision, right? Including being that preferred community, that home for radiation safety professionals. So I want to sort of bring people in to HPS. So I want to personally invite those of you who are chapter members and not HPS members to really consider joining HPS and invite your friends. I also it's not just about numbers for me. I also want to increase member engagement. So I want to get more people to volunteer and newer people to volunteer so that we can have people who are members of HPS engaged in HPS activities. So we have a lot of core services. Ask the Expert, we have the journal, we have our meetings that we put out. We've got a lot of core services that we deliver. This is how we keep our members. And this is how I want to make sure that we keep our members because they are satisfied with what we are offering today. I also want to make sure that we maintain these public resources because we have thousands of hits every month on the HPS website looking at Ask the Experts. So we have members of the public from all over the world who are coming to us with their radiation safety questions. And I want to make sure that we continue that and reach out. Finally, you can expect me to hear whatever feedback you have, whether it's positive or negative, right? So if you've got praise or criticism, I'm going to hear what you have to say, and I'm actually going to listen. So it's going to go in the ears and then rattle around in there for a while. Okay. All right. So I'm going to end with what do you want from HPS? So please give me some feedback and I realize that I've been talking for a long time, so we may not have time, given your agenda, to get feedback now, but use the email, president-elect@hps.org. And I want to thank you all for your kind attention and the kind invitation to come and speak with you tonight. So with that, I'll turn it back to you, Brianna and Bridget.
Thank you so much, Mike. That was a great talk, and thank you so much for becoming president. I'm looking forward to your tenure. You've got good energy, and you're super knowledgeable, and you've got amazing experience. So you're the best.
Well, thanks. I'll try not to let you down.
Um, what did we? Okay, so Bridget is next up with a couple of comments on membership. Perfect.
All right. Thanks,
Yep.
Brianna. I did put the agenda in the chat because I know it's not super big because I wanted to fit it on all on one page. Feel free to save that Google Doc. I'll also try and send it out as minutes with a PDF. I took some notes on Mike's excellent talk. So basically, I'm just here to talk to you a little bit about your membership and some plans we have for the future with members. Please consider paying your dues. It's only $20. And what we use that money for is primarily, frankly, to provide refreshments so you can go to a meeting and not be skipping your dinner. And then just in the event that for some reason we need to rent a space, like when we were at UCSD, we had to do both room rental and refreshments. That's why we are so incredibly grateful for Ron that he's going to help us out. And Mike also hosted us, which was Mike Moran at Polypeptides Inc., which was wonderful. And then also, if you know of any company that's radiation related, that would like to participate in HBS, please have them contact us. After I'm done talking, I'll put our email in the chat, and you've received multiple emails from us. The leadership met this December, and we came up with some benefits for affiliated members. So we have always had this little pull down in payment that says if you pay us $100, your company can become an affiliate member. We did some brainstorming, and some possible benefits of that we're going to give people opportunities to sponsor a meeting and to provide, we promise, a very short amount of information about their goods or services that are shared. We are going to provide shout outs on our social media page. And occasionally, we in the past have had some really dynamic corporate speakers coming in and giving a rich talk like the one Mike did, like one that was given by Philotechnics a few years ago. I still reference quite often in my my RSO classes. So we're going to work with affiliate members and see if they have that kind of quality talk to provide for us, because we are always looking for speakers. And so it would be great if we could expand the pool of potentials. Also, Joel, I don't know if Joel's here tonight,
Yeah.
but he was very excited about the idea of us sponsoring a science fair award. And we would be happy to have, if we're going to investigate, we think it would be possible to have a co-sponsor for that. So your company sponsoring the San Diego Health Physics Society Science Fair Award. I know Joel has offered to judge. But if you are interested in also being a judge for that, I think we need to provide a few specific judges if we're going to sponsor an award. So keep an eye out for communications about that. And I've included the hpschapters.org website, which HPS has been kind enough to um, help us put together. And Chris, our former president, who was very internet savvy, also has links on that page to Facebook, LinkedIn, and Twitter. I'm not as good at posting on Twitter because you can't post like the Zoom link for a virtual meeting, but I'll try to post for in-person meetings. But Facebook and LinkedIn are my primary ways that I communicate with you, unless I take the time to send everybody an email. So please go ahead. If you are a brand new member, I think there's this little survey form we would like you to fill out. If you are just ready to pay dues, you just click on the pay dues section. And as you can see, member, if we have any students out there, you only have to pay $10. And then our affiliate membership is $100. So as I said, spread the word, get your dues in. It also helps me as a secretary, as was referenced by Mike, I need to fill out a report and say how many members we have. And we have a lot of people on our list, but not all of them are dues paying members, and not all of them maybe are still around. So we'd love to update that and just have a really vibrant community. And Brianna, why don't you go on and talk about the other things that we have planned for 2025?
So 2025 is going to be a great year. So thank you, Bridget. Um, First of all, as Mike and Bridget, I think, mentioned, um, HPS National has requested a chapter rep be appointed to attend the quarterly meetings of all the chapters. If anyone is interested in doing so, please let us know. And if anyone's interested in joining the leadership as a president-elect or director liaison, also let us know. It's a lot of fun. I won't lie to you. Bridget's the best. So I can't guarantee that she'll also be on the leadership team. However, I can guarantee we are leaving it better than we found it. So yeah, we would also like to turn over since last year's social meetups, we're at like the best attended from our point of view. However, we figure if you guys would like to organize some social meetups, if anyone's interested in hosting, um, if anyone just really enjoys parties, and throwing parties, I would love that. Um, I would do it, except I live in a tiny apartment. But if anyone is interested in attending the quarterly meetings, turn doing the social meetups, or joining the leadership, please let us know. Just shoot us an email real quick. We're super available. As for this coming year, in addition to that, we have a tentative meeting in March. We're like 90% sure it's going to be March 20th. It'll be at 7 p.m., hosted by the Department of Environmental Health and Quality, right here in San Diego. Dr. Daniel Skanderberg will be speaking about innovations in radiation medicine and InfraGard. It's a cool topic. It's a really cool talk. So I definitely want to see everyone there. I would love to see everyone there. June, we are working on an online meeting. We do not have a speaker yet. So if you have some cool topics, some great stories, or if you know someone who does, let us know. Ken is raising his hand. What's up, Ken?
Yeah, I had one suggestion. I can't take credit for it, but it came out of a discussion when we were meeting at um, the polypeptides building. When we were walking through, we were kind of having a conversation, a pretty kind of fun conversation about what we thought was the best, like multi-purpose survey meter or the best utility meter out there. And I thought it would just be really great to do a like a member discussion where we each kind of maybe bring and show and tell our various meters and why we like that one best or why we think that's the better instrument for whatever case. There's a lot of new technology out there. I know a lot of people have kind of their favorites and really think it's there. I think we could benefit from something like that.
So
Yeah,
do we
definitely.
want to do that virtually, Ken, or in person?
I think in person is always kind of neat because you can play with them a little bit and you can
Yeah.
kind of see like,
Okay.
well, I see what you mean, like why that's better than my old trusty old Ludlam 3, and maybe I should move on to modern tech.
Excellent. Okay.
Yeah, that does seem like it would be better in person.
So instrument, show and tell, date, TBD.
Hey, Brianna,
Sounds
this is
good.
Mike.
Hey,
This is
Mike.
Mike. How you doing? Hey, I'm just
Good.
wondering on the website we have for our chapter, could we post the meetings there? Because I don't do social media. I'm a strange bird.
Well, Mike, that was actually my main 100% request for the chapter website is if there's a way that we could, in addition to posting our social media, just kind of like you guys have upcoming events, it would be nice
Yeah,
to be able to put that together.
yeah, that'd be great.
Yeah, right now
In the
all we like if you don't do social media, we've got the email list, but which
yeah.
I assume is how you're here.
And in the meantime, Mike, just email me if you ever want to know what's up, and I'll email you back, but probably my personal email versus the San Diego HPS one.
Cool. Um, Yeah, so we are still looking for speakers for our online meeting in June. So if you have any stories or know anyone who has a great topic, um, please let us know. Just shoot us an email. Like we've been saying, we're super available. We do have a speaker for our August in-person meeting. It's Dr. Andrew Karam, Radiation Protection Sea Stories.
Karam.
Karam. See,
Uh-huh.
I just mess up names.
No worries.
However, the topic also super cool. Sea stories for radiation protection is super super cool stuff. We do not have a location yet, but we are looking into it, and we would appreciate any leads. So yeah, if you have any ideas, any feedback, anything, please let us know. And I believe that's it.
That's a wrap. I know usually we do like breakout rooms, but I knew this was going to go kind of long because of all the great information Mike was sharing. So today, that's not something that we'll do in future meetings. If we have kind of a more succinct agenda, we'll go back to that because I personally really enjoyed it. It's funny. Renee was talking about Jake, and I'm like, oh yeah, I know Jake because he was in my little breakout room and I got to know him really well. So I hope to do that in the future, but today I just know we've all had a long day. We've all been quite stressed about the wildfires. I know poor Ken, like every day it's like, is it going to hit UCLA or Riverside or San Diego? So we need a break, but I'm looking forward to doing that. And once again, if anybody is like super jazzed about doing the social meetups, we did have one that was really successful. It's just a lot to do on top of organizing formal meetings. And if anybody wants to join me at that regional chapter meeting and just be kind of an adjunct person, maybe show up at leadership meetings, but don't have specific responsibilities yet, maybe just kind of be in the wings. That would be really nice too. Because I hope we have Brianna forever, but what if she like gets a job somewhere else, she is this go-getting early career professional. So I'm trying to grow our leadership team a little bit. So I think that's about it. Does anybody else have any other business? All right. Well, we will see you in March. Please come. It's going to be great. I'll try to arrange some kind of refreshment that is not pizza. We will do our best since we're not paying for both the room and the food. I think we can do that. And we look forward to seeing all of you in person. And Ken, I'll get working on that instrument show until I have some ideas. So, all right, everybody. Thank you. Good night.
Bye bye, everybody.